The next problem up again, I'm trying to solve this equation in the complex plane. I should get the same amount of solutions as a power, always. Z to the fourth equal 1 minus I, so isolate that. As it is, fourth root of 1 minus I doesn't mean much, but if I am to go ahead and figure out what that is in polar, take 1, a negative 1, I know that's radical 2, so Z to the fourth equal radical 2e, and I know the reference angle is pi over 4, but in the fourth quadrant that's 7 pi over 4. Since I want 4 solutions, I add 2 pi k. I find the general solution, something we've been doing all along. And if I proceed and take the fourth root of both sides, that's raising both sides to the 1/4 power. That is radical 2, or I should say even better, 2 to the 1/2 e to the 7 pi over 4 plus 2 pi k I, all raised to the 1/4 power. And Z sub k will equal, if you multiply the powers, that's 1/8 e to the 7 pi over 16 plus 2 pi over 4k I. So very important to find the general solution. And from there, what we would do, we would say, let's find Z sub 0, Z sub 1, Z sub 2, and Z sub 3. And we're done. Put 0 in for k, that's 2 to the 1/8 e to the 7 pi over 16. Let k equal 1. 2 to the 1/8 e. What is 7 pi over 16? Plus, if I make that over 16, multiply by 4 top and bottom, 8 pi. That is 15 pi over 16. I'm forgetting the I. 2 to the 1/8, you notice you added an 8, add another 8, 23 pi over 16i, and 2 to the 1/8 e, another 8, that will be 31 pi over 16i. If you add another 8, you will get 39 over 16. Take 32 out, you're repeating. And if you want to graph that, and you are going to be asked to graph that, depending on which book you took, ours does. What I want to break this into 16 pieces, so 8 pieces each, right? So if I was to go ahead and break it up, that's breaking it into 2, breaking each of those into 2, that's 4. I want 8, so break each of those into 2. Halfway, and break those into halves. Halfway, break those into halves, and each of those into a half. Halfway, break them into halves, and halves. This is 1 pi over 16. This is 2 pi over 16. Now, in this case, the radius is the 8th root of 2, very small. But I need 7. So 1, 2, 3, 4, 5, 6, 7. Let me label it with a different color. 1, 2, 3, 4, 5, 6. At least you should label those. Then 15, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then 16, 17, 18, 19, 20, 21, 22, 23. That's not right. 16, 17, 18, 19, 20, 21, 22, 23 is right there. My mistake. And add another 8, 23, 24, 25, 26, 27, 28, 29, 30, and 31 pi over 16. Again, you don't need to put the arrow, the lines, the points are good enough. but normally it looks like this. And you notice those are 90 degrees apart, which is pi over 2 apart. And this is the 8th root of 2, the length of that. You don't need to label the length, you just need to label where those are. And here we are. The final application. Find the indicated roots, multiple of them, and graph the roots in the complex plane. The cube roots of 1 plus I, the same deal as before. What you do, if I want the fourth roots of 1 plus I can't find 4 solutions. That really means they must have had z to the fourth equal 1 plus I, and they're trying to find the 4 solutions. But normally that's how it's stated. Normally it's stated as roots of unity. That's what this is. A very powerful application that we need. Well, go 1 to the right, 1 up. We know this is radical 2. So I could write this as radical 2 e to the pi over 4, since I want 4 roots plus 2 pi k I. That was DeMoiver's theorem, by the way. But if I use e, I could save myself all of that pain. So DeMoiver's theorem says, if you take the cosine of theta plus I the sine of n theta, of theta, and you raise it to the n power, that's the cosine of n theta plus I the sine of n theta. And if you want more solutions, you would say that's the cosine of n theta plus 2 pi k plus I the sine of n theta plus 2 pi k. Well, look at it this way. If I write this as e to the I theta and raise it to the n, isn't that you multiply the powers? And isn't this the cosine of n theta plus sine of n theta? So I don't need DeMoiver's theorem if I'm using Euler's formula. That's saving me memorizing all of these formulas. Well, what do we know? We want the fourth root of this. We want to take square root of 2 e to the pi over 4 plus 2 pi k I and take the fourth root. Well, the fourth root is really raising this to the 1/4 power. Isn't that how it works? And that means I'm looking at 2 to the 1/2 times 1/4, that's 1/8 again, e to the pi over 16 plus 2 pi over 4 k I. So this is actually my z sub k, and to find the fourth root, let k equal 0. You'll get 2 to the 1/8 e to the pi over 16I, let k equal 1. You get 2 to the 1/8 e to the, and what do you notice? If I make that an 8, that is 8 plus 1, 9 pi over 16I, k equal 2. You will get 2 to the 1/8 e, add another 8, 17 pi over 16I, and k equal 3. You get the last point, 2 to the 1/8 e, add another 8, that's 25 pi over 16I. If you add another 8, you'll get 33, which is 1 past 2 pi, and it's right there. And if I put that on a grid, I'm looking at breaking this into 16 pieces. This is 2, this is 4, and we do it again. This is 2, this is 4, and if you break each of those into 2, that's 8. This is 2 halves and half of each. This is 2, break it into halves, and just label the first one as pi over 16. No problem, you just need to label the main points, and the main points would be pi over 16, right there, it's already labeled, 9, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't forget to add the axis. That is 9 pi over 16. The next one is at 17 pi, so that's 1 pass. Remember, pi is 16 pi over 16, so it's right there, 17 pi over 16. and another 8. 1, 2, 3, 4, 5, 6, 7, and 8. And that is 25 pi over 16. No need to put the lines, but if you want, you could label 1. You don't have to. That's 2 to the 1/8. That's the length of that, the 8th root of 1. Again, those are called roots of unity. You need that in differential equations. And in linear algebra, you call those right there eigenvalues. And you find the eigenvectors associated with those. Tons of applications. 2 more to go. I'm trying to cover all bases, so no matter what you come across, you could solve. I want the 5th roots of z to the 4th of 4i. You could write z to the 5th equal 4i if that helps. That's really what it is. So this one doesn't require much work because I know where that is. 4i is right there. You go a distance of 4 and you move pi over 2. So I could say z to the 5th equals, or I'm taking the 5th root of this, however you want to see it. This is really 4e to the pi over 2. Since I want more than 1, I always add 2 pi k. You could do that any time, but normally you repeat unless you want more solutions. Now, z is going to equal, I'll take the 5th root of both sides, that is 4 e to the pi over 2 plus 2 pi k I. So that is z sub k again. If you don't introduce z, you don't have to. This is 2 squared. Or I could say the 5th root of 2. That's okay. That doesn't matter. E to the pi over 10 plus 2 pi over 5k I. You want 5 solutions? Let k equal 0. Let k equal 1. Let k equal 2. Let k equal 3. And let k equal 4. And here I will get 5th root of 2 e to the pi over 10i. 5th root of 2 e. If I make that over 10, that's 4 pi over 10. Right? Plus 1, that's 5 pi over 10. You could reduce those if you like. So you added 4, add another 4, 9 pi over 10i. Add another 4, e to the 13 pi over 10i, and another 4. That's e to the 17 pi over 10i. And if you add another 4, 21 over 10, 21 pi over 10. That's more than 2 pi. That's the same as pi over 10. Now comes our graph. A very important topic. Annoying a bit, but you can get the hang of it. So now if I go by and I split this into 10 pieces, this is 1 pi. I need to make this whole thing 10. So I need to make this 5 and this 5. 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You don't have to get a protractor and figure this out. That's okay. Approximation is accepted. And the first one is at pi over 10. I label that clearly. That is pi over 10. That's the first one. Add another 4. 1, 2, 3, 4. We do know that pi over 10 is really pi. 5 pi over 10 is pi over 2. You want to reduce it, you can. 9 pi over 10 is 1 short from 10 pi over 10. 1, 2, 3, 4. And 1, 2, 3, 4. For the purpose of our class, that's all they want. You could extend 1, you don't have to, and say that is the 5th root of 2. And I have one more example to make sure that I covered every possible scenario you can come up with. And that's the last problem we have. So here, if I take this, the same thing, I want the 6 roots. So let's take 6 root of 2. That's not pretty. 6 root of 2 minus 2i. You know what? Let me do 3. Just want to show you how 3 works. Third roots. So let's take, again, you could break this into whatever you like. 5 roots, 7 roots, the work is the same. Of 2 minus 2 radical 3i, that doesn't mean much. What we do, we convert that to polar form. Now I saw this in engineering mathematics as well when we were doing residues. So you go 2 to the right, negative 2 radical 3 down, and that makes r squared equals 4 plus 4 times 3, that's 16, so r equal a 4. So this is going to be the cube root of 4e, and tan of theta equals negative 2 radical 3 over 2, which is radical 3, and what would that be? 60 degrees. So the reference angle is pi over 3, but in the fourth quadrant, that is 5 pi over 3 plus 2 pi k I. So this is actually the cube root of 4. E, you raise that to the 1/3 power, that's 5 pi over 9 plus 2 pi over 3 k I. And here you let k equal 0, k equal 1, and k equal 2, and you're done. So k equals 0, I get the cube root of 4 e to the 5 pi over 9 I. K equal 1, cube root of 4, if I add those, multiply by 3 top and bottom, that's 6. That is 11 pi over 9i, and the cube root of 4 e, another 6, that is 17 pi over 9i, another 6, that will be 23, bigger than 18 pi over 9 by 5, and there it is. So I get my circle. Remember, you could draw this as big as small as you like, but you just need to label properly. So I need to break everything into 9. This is 1 pi, 9 pi over 9. I need to break this into 9 equal parts, right? So here I can't go evenly. 1, 2, 3, 4, 5, 6. That didn't work. Oh boy. Okay, 9 parts. Yeah, I gotta do a bit more. So 1 or 4.5, 2, 3, 4, there you go, 5, 6, 7, 8, 9, and again 4.5, 1, 2, 3, 4, that's the half, 5, 6, 7, 8, and 9. So again, it doesn't have to be perfect. All what you need to do now is label for me 5 pi over 9, 1, 2, 3, 4, 5 pi over 9, 11, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. And as you see, if I add 2 more, I'll get, oh, something's not right. I counted that I shouldn't have. It's right there. The 17 pi over 9. Again, this was, oh, this I don't need. You just need to label one of those. You could put it that way if you like. You don't have to label any of those. I just need the angles, but you could label one if you want and say that is the cube root of 4. And that's pretty much the full application of this. When the time comes and you see this in use, that's going to be a long way. You're not going to see this until you take linear algebra or differential equations. And that would be it for this section.